So today's going to be shorter than it should be, shorter than I want it to be. And the reason is that I have an extra big demo show for tomorrow, and there's a lot of stuff that's just not working. So I'm looking forward to dealing with it once this class is over. But I already decided, and I'm going to follow through with it, that we're going to go through 2 units today. We're going to go through low mass stars, which is unit 10. And we're going to go through high mass stars, which is unit 11. The unit 11 homework is just canceled. It's just gone. I'm not going to grade it. You guys aren't going to submit it. It was short anyway. There's one big point I want to make about high mass stars to you, and I'm going to make it. And then we're going to consider the topic more or less closed. Low mass stars, we're going to go through in a little bit more detail, and that will be a live homework. So y'all will do that and turn it in. Now, we've reached a point where I'm going to be extremely squishy about due dates. I'm behind, and I will not insist on due dates for students when I am behind. So if you need more time, what you need to do is let me know. By this point, everybody has, I hope, read over the document that deals with the final exam. So it's a non-traditional final exam, and you all need to figure out what you're going to do and rattle me off a proposal, because it's going to be worth points. Any questions over that, or indeed over anything? This is the most important part of the course, the bit where you.
In which module is that located in? I was having a trouble.
It's in, let me double check. I believe it's in a module called Final Exam. Yeah, it's in a module called Final Project. Can you see it? Oh, I'm sorry, it's called Final Project Spring 2021. So I'm going to wait because this is pretty important. Go ahead and check Canvas. Is that file showing up for you?
Would it be located in the upcoming assignments?
No, I haven't created an assignment category for it yet beyond the assignment category of proposals. Let me double check that that is visible and accessible to you. Should be, but let's be sure. All right, final project actually is published. It's out of 40 points.
I found it.
Oh, okay. And just for my own peace of mind, there should also be a final project proposal category that I'm not currently seeing. So I'm not sure what happens to that, but it obviously needs to exist. And so I'm going to make it exist right after this class is done. Any other questions over anything? All right, I just counted to 5 in my head. Y'all are good to ask me questions at any time during this class, but we are going to proceed forward. Assuming the technical difficulties do not interfere, we are going to proceed forward. All right. Element of the day. We talked about fusion, which is when light elements merge together. You take 4 hydrogen atoms, combine them together to be 1 helium atom, and the 4 hydrogen atoms weigh more than 1 helium atom. That missing mass gets turned into energy. E equals mc squared. Not a true equation, by the way, only a true equation if the object isn't moving, but that's fine. We can consider it to be true for the point of view of this class. So for the fusion side of things, light elements combine, energy is released. That is not, however, the whole story of how you get energy out of atoms. There is another way. It's called fission. Fission is when you take heavy. By heavy, I mean anything on the periodic table of elements kind of has the element iron. And that's when heavy elements break apart and release energy. It occurs to me that I have the PowerPoint enlarged and the screen not. So here we go. Fusion, light elements combine, energy is released. Fission, heavy elements break apart and release energy. So let's look at the implications for that in our pretty recent history. There's a particular isotope of uranium, uranium-235. So uranium has 92 protons. So subtract 235 from 92, subtract 92 from 235, and you have how many neutrons that particular version of uranium has. Uranium-238 is way more common, but the nice thing about uranium-235 is it is very, 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 very close to falling apart. It takes only a slight nudge, and that particular isotope will break into 2 pieces. Because it's on the heavier side of the periodic table of elements, it will release energy when it breaks into pieces, as opposed to releasing energy when it's combined. This is how you make a nuclear bomb. This is how you make an atom bomb, which is the first pass on nuclear weapons that humanity achieved for a number of years. There's other sorts. There's hydrogen bombs, in which hydrogen is combined to form helium, which releases energy on its own. But those bombs require the temperature to be so high. Remember, the core temperature of the sun is 100 million Kelvin. And by the time you say a number like 100 million, who cares what the unit of Kelvin is? It's obviously really hot, really hot. So in order to make a hydrogen bomb work, you have to set an atom bomb off right next to it. So hydrogen bombs aren't a clean version of destruction. They still involve an immense release of radioactivity. And fusion power, the power by which we could combine hydrogen into helium, is not an accessible form of energy because we just can't reach those temperatures without, for example, setting off an atom bomb right next to the reactor. Now we have fusion reactors. There's reactors out there that combine hydrogen into helium. but they all take more energy than they release. So that's not particularly useful as a reactor. Every nuclear reactor on the planet that works and provides energy involves taking either uranium or plutonium and breaking it apart. The problem with breaking a heavy element like this apart is that when it falls apart, there's daughter products, which create daughter products, which create daughter products. And every time an element decays, it emits radioactivity. And so that's why uranium-235 is such a big deal, because you can make an atom bomb out of it. But when you do, you create daughter products, and they just keep on decaying for a real long time. And they emit radioactivity the whole time they are. Okay. Evolution of low mass stars, white dwarfs, binary stars, novae. I looked at the homework before I decided what I was going to teach us. So I'm going to hit the highlights of the homework, and there's much of the rest of it that I'm going to skip because of breaking beakers. I apologize, but I imagine that there's many of you that will not be too unhappy to get out of here a little bit early. So, stars can't live on the main sequence forever. The main sequence is when hydrogen in the core is being combined to form helium. Eventually, you run out of hydrogen in the core. And also, the core is so hot and has been so hot for so long that it's bounced all the accessible hydrogen away from the core. So it's pretty much had to rely only on the hydrogen that was in the core to begin with. Once all that hydrogen is gone, it's gone. So as an analogy for how we learned about stars, imagine going to a football stadium and taking 1 minute to observe all the people there. What you observed in that 1 minute, did you learn about the human life cycle? You've learned that people like sports. But now imagine that you're looking out at stars and you've only been able to effectively look at them for about 50 years. Stars live in between 100 billion years to 1 million years. So even the shortest lived stars have only been observed for a very short period of time. The only way astronomers know anything about stars is through inference. We look at stars with similar amounts of mass, with similar amounts of light coming out of them, and then we work backwards to create categories and associations and try to puzzle out what's happening from there. So the very biggest stars die super fast. O-type stars live for only 1 million years. This is useful for light because the very biggest stars are the stars that expel the most complicated elements. If you want an element like uranium, you need an O-type star to explode. Or you need 2 dead stars to collide with each other. Both could be adequate for making a heavy element like that. On the other hand, the very teeniest, tiniest of stars live for only 500 billion years. The universe itself has an age that's argued over by astronomers, but it's comfortably predicted to be about 17 billion years old. Consequently, what happens to an M-type star when it dies is entirely theoretical. No M-type star that has yet to come into existence has died, period. They live far longer than the current age of the universe. So why do big stars die so fast? They got more fuel, but they tear through it more quickly. In general, almost all stars in the universe count as low mass stars. They aren't O-type stars, they aren't B-type stars, which are the 2 star types that count as officially high mass. Those are the only stars that go supernova. And supernovas are really essential for spreading heavy elements throughout the universe. And also for shocking nebula, which are big clouds of hydrogen spread throughout the galaxy so as to make the gas clouds compress and cause additional starburst, which is enriched by the heavy elements the supernova themselves have spat out. But they don't live long. It's hard to see them. There's only one big star that's going to go supernova that you can see on Earth. And we, in Napa Valley, California, or in Berkeley, California, can't see it at all. It's called Eta Carinae. It's only really visible from the southern hemisphere, or from close to it. You can see it from the equator. Because when a super heavy star explodes, it creates jets of energy that are expelled from the North and the South Pole. If Eta Carinae's poles were pointed towards us, we would have a death sentence. Like, it would eventually go supernova, it would create those jets. The jets would hit the planet Earth. They would at least destroy the entire ozone layer. And the ozone layer blocks a lot of the high energy radiation from the sun. And it would probably do worse things to us than that. Fortunately, Eta Carinae's poles are not pointed towards us. So when it finally goes off, we will be spared. But it's significant that there's only one major star like that we can see from the planet Earth. They're exceptionally rare, not only because they don't happen often. Only 3% of about all the stars that are born are stars like that, the super heavy stars. But also because they don't live long. All right, time passes. The core is going to fill up with more and more and more helium until a point is reached where there's no more hydrogen at the core. So what then? If no more hydrogen left to fuse, there is no more heat coming from the core. The way a star exists is the radiation pressure pushing outwards is balanced by the gravitational force pulling inwards. With no more radiation pressure pushing outwards, gravity very quickly starts to win. So the star gets smaller and smaller and smaller. As it gets smaller, it's also getting hotter and hotter and hotter. Until finally, there is an entirely new kind of pressure that resists the gravitational attraction. This is a quantum mechanical effect. We don't have to make too much of it. We don't have to learn quantum mechanics, but it is a quantum mechanical effect. So, a person named Fermi said that atoms and particles and everything that has a spin of 1/2 or 3/2 or 5/2 doesn't want to share space with something else of an identical spin. Electrons happen to be what's called a fermion. They have a spin of 1/2. And so they don't want to share space with another electron that has an identical spin. They just don't. This is a quantum mechanical effect. So as the star contracts, it reaches a point where in the core, we've got all those little helium atoms. That's pretty much all that's left. But if it compressed to the point, the electron shells are all touching. The electron shells are a lot bigger than the nucleus of an atom. The nucleus of an atom is here, and it's got the protons and the neutrons. And out here we have the electron shell. So the star's core has been compressed quite a bit, but not nearly as much as it could be. From the point of view of physics, this is still a lot of space. As a comparison of the size of a nucleus to the size of an electron shell, if the electron orbitals were the size of the Earth, The nucleus would be the size of San Francisco. So it's still mostly empty space, but it's much more compressed than it was before. Previously, the negative shells that are surrounding all of these helium atoms wouldn't have anything to do with each other. They're zipping around, there's a lot of space in between them, but this enormous pressure, the enormous force of gravity has made them be close enough that all the electron shells are touching. They can go no further because electrons refuse to share the same quantum mechanical state as other electrons. And that is the new thing that's holding the star up. This weird quantum mechanical effect. The core of the star will be compressed no further because the electron shells of the individual helium atoms will not cross each other. So you've got your helium core, and another word for when the electron shells are all touching each other is degenerate. And then around that, because it is super, super, super hot, we get a new source of energy. We have a helium core, but around that, there is a shell where the hydrogen that's available from the rest of the star is burning into helium. And that is generating energy the exact same way that the core used to generate energy via that process. And then, I don't know, there's another rest of the star out here in various directions. It is very, very, very big in comparison to what's happening in the core. This is the red giant stage. This is what's going to happen when the sun eventually swells up and swallows Mercury and Venus, and perhaps Earth. Although recently people have been speculating that likely the sun will have lost so much mass by the time it gets to be that big that Earth will have shifted out in its orbit to the extent that it won't quite be fully engulfed. On the other hand, even the planets that aren't engulfed will not disappear instantly. My physics students asked me how long the planet Mercury would exist inside the sun once the sun had completely enveloped it. And so I did a bunch of calculations and I figured out that Mercury would exist for about 40,000 years before it completely is destroyed. That's not nothing. Okay, moving on. So we've got a helium core where all the electron shells are pressing against each other. We've got a hydrogen burning shell. Outside of that, there's a bunch of hydrogen that's just being pushed outward by the radiation pressure. The sun's gotten huge. There's no fusion happening. The sun gets bigger and bigger and bigger, or the star gets bigger and bigger and bigger. And we end up with a kind of cycle. So we've got this helium core where the electron shells are all pressing against each other. Another word for which would be degenerate. And that leads to a lot of gravity pushing down on the core, which is creating the hydrogen shell around it that's burning into helium. But the more pressure that's applied to that shell, the more rapidly it creates helium. The moment it creates helium, that helium just falls into the core. So the core gets bigger and bigger and bigger and has more and more and more helium. And that leads to even more gravitational force, which makes that shell that's burning hydrogen into helium even hotter than it was before, which leads to a faster conversion of hydrogen into helium, which then falls into the core and creates an even more massive core, until finally something changes. And by the time something changes, the stars become huge, 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 huge. Here's what the star will look like as a red giant. And that's what the star looks like now. So it will definitely envelop Mercury and Venus. It will probably, but maybe not envelop Earth. Earth will definitely shift its orbit out. It likely won't envelop Mars, but Mars is going to basically be cooked out. Interestingly, there is one moon in the solar system that is extremely like Earth in terms of what its composition was. Like the moon Titan, in orbit around Saturn, has essentially the exact same chemical composition that Earth did before life started on it. And so when Titan finally heats up, there may be a second chance of life in the solar system, but the sun spends so little time in the red giant stage that if life does get started on Titan, it's going to be a bit of a tragic story because it won't be long-lived. So eventually things in the core get so hot that the helium starts to combine with other helium. When that happens, things happen on the HR diagram. And for our purposes in the class, the main result is that 4 helium turn into 1 carbon. And so the core is becoming carbon. And that's generating energy. This is a generated energy when 4 hydrogen combine to be 1 helium. So that's what the process looks like. And now we have 3 different layers. We've got helium turning into carbon in the core. Hydrogen is fusing into helium in a shell around the core. And then there's a big envelope beyond that. This stage is not going to last for very long. So the phase at which there is a hydrogen to helium burning shell for a star like the sun will last for about 1 billion years. Again, this is inference based on other sun-like stars we can observe. And then once the helium core starts to combine to form carbon, that's only going to last for about 100 million years, which is a blink of an eye. Dinosaurs went extinct 65 million years ago. They evolved 300 million years ago. We're starting to talk about the behavior of stars in terms of timelines that could be understood in terms of the lifespan of species. That's very fast. Okay. I'm going to skip most of this until I get to the real heart of the matter. Eventually, the core is very, very hot and the star is extremely large. The result of that is that the star starts to jettison a lot of its outer material. Now, this is nothing new. The sun is constantly losing mass. That's what the solar wind is. That's the sun spitting off its own outer layers into the solar system. But now a star is jettisoning almost all of its mass, or at least almost all of its volume. And by the end of it, only the core will be left. This is called a planetary nebula. For all purposes, it's just like any other nebula. It's just a nebula that's generated by medium to little sized star going through its death throes. They look like this. They're very differently shaped from each other. This is probably due to complex magnetic fields inside of stars, but I would like to believe that it might theoretically be due to the fact that as these stars expand and develop planets, the planets don't instantly get destroyed. They kind of move around the atmosphere of the star and stir the interior. And so even though it's probably not the case, I would like it if the reason behind the vast number of differences of planetary nebulas was that planets are stirring the stars and resulting in matter being thrown off in a number of different sorts of ways. Okay, you're not going to draw a couple of planetary nebulas. I'm not going to show you the Ant Nebula and Lagoon Nebula. I've learned my lesson. If I play YouTube videos, YouTube will not allow me to upload them. These files are all available as a PDF. I urge you to go and watch every embedded link, because I didn't choose them casually. They're great, but I can't play them in class anymore. More planetary nebulas. And this picture is included just to show you how astronomers actually construct an image. We don't take pictures the same way your cell phone takes pictures. The way that astronomers take pictures, they use filters that let through only one kind of light. These filters are extremely expensive to produce, ridiculously expensive. But we center them around different colors of light that indicate different types of elements. So top left, this indicates hydrogen. Top right, this indicates oxygen. Bottom left, this indicates ionized helium. And then you put them all together and you choose a false color palette. And that's your new image. Almost all pictures in astronomy involve choices of false color palettes. None of these things are like they'd actually appear if you could go out there and see them. More planetary nebulas, more planetary nebulas. Here I'm just trying to hammer home what kind of diversity of shape there is out there. Low mass stars die and expel their matter in really interesting ways. But once they're done dying, they all meet more or less the same end. So at the very end of this process, you've got some hydrogen on the outside that's not burning, some hydrogen in a shell that is burning into helium, some helium below that that's not burning, some helium below that that is burning and creating carbon. And then you've got a core that is mostly carbon, a little bit of oxygen, and it's not hot enough to make that core burn. It can't make carbon burn in a star the size of the sun. So what happens is that all these layers generate a tremendous amount of heat, and most of the space of the star, the volume of the star, gets jettisoned into outer space. The star itself, or the remains of the star, shrinks down slowly as layers get tossed off. And as the star shrinks, it generates less and less light. It's hot, but it's tiny, and consequently hard to see. And we have a name for this kind of. I'm going to put star in quotes. It's not really a star anymore. We have a name for this kind of stellar corpse. We call them white dwarfs. They're extremely difficult to detect because they're super tiny, but they're super hot, and they're comprised almost entirely of carbon, a little bit of oxygen, and then there's a crust with a few other elements, but it's just a crust. It's almost entirely carbon and oxygen. They're supported via electron degeneracy pressure, exactly like the core of the sun will be when it leaves the main sequence. So in the center of every white dwarf, we have carbon atom, electron shell around the carbon atom, electron shell around the carbon atom, electron shell around the carbon atom. So this is a crystalline structure, a more tightly bonded crystalline structure than anything you'll find on Earth, but it's still a crystalline structure. Carbon in a crystalline structure is a diamond. So the company De Beers has artificially restricted the supply of diamonds on Earth in order to make money. In fact, diamonds are super common on this planet, but they are also the most common form of star quarks is left after a star dies. Diamonds truly are common. Most stars die and leave behind a white dwarf. A white dwarf is basically a huge diamond. So I don't know if diamonds are forever, because sometimes white dwarfs combine and collide with other objects, but they sure are common. All right, so when white dwarfs form, they're hot. They're small. They're about the size of the Earth, but they have about half the mass of the sun. And they're dense. If you were to take a normal six-sided die, it would weigh, made out of a white dwarf, it would weigh over 5,000 pounds on the Earth. And they're inert. They don't create energy anymore. There's no fusion happening inside. Now, sometimes they're lucky enough to get an energy source. If a white dwarf passes close enough by some body of gas or another star, then it can pull that gas onto itself. And it's so heavy, it's so massive that when that gas gets pulled onto the surface, it immediately undergoes fusion. That's called a nova. We'll review that again at the end of the class. Okay, the end of the class came sooner than I thought, the end of these slides. So most star systems are binary star systems. Our sun is a little bit unusual in that there's only one of it. And there's always going to be a heavier star and a lighter star. The heavier star is going to get big and then die. It's a white dwarf before the smaller star does. So once one of the stars becomes a white dwarf, you end up with a situation where the other star is hanging out just being a normal star, but the white dwarf is still nearby. When the star that is still a normal star begins to go through its death cycle and swells to become large, then it gets close enough to the white dwarf that the white dwarf can start to siphon mass off of it. It's pulling the other star to pieces. And every little bit of mass that it pulls off the other star goes onto its surface, undergoes fusion, and there's a bright flash of light. That's a nova. But there's more going on here than just a nova. So pulling a little bit of mass off makes the flash of light great. But there is an effect that is much, much, much more dramatic. If a white dwarf can acquire enough mass that its net mass is about 1.4 times the current mass of the sun, then electron degeneracy pressure is not enough to keep the star from collapsing. At 1.4 the mass of the sun, these electron shells shatter. Boom. I can't say if this is bad or good or whatever, it just is. When the electron shells shatter, under these conditions, the entirety of the star gets turned into energy. It doesn't turn into a black dwarf. It doesn't turn into a black hole. It doesn't turn into a neutron star. It doesn't turn into any kind of object that you might have heard of. It's associated with a stellar corpse. It just explodes. It's gone. So this is highly useful to astronomers because of this, because white dwarfs have this happen to them at 1.4 times the mass of the sun. We think very reliably. That means that we can use E equals mc squared and calculate exactly how bright a white dwarf is when this happens to it. It's called a type 1a supernova, and it certainly is a supernova. So a type 1a supernova can shine 10 billion times brighter than the sun. When a star in our galaxy goes supernova, it is so bright it can be seen during the day for several months, and at night it is as bright as full moon. These objects are very far away. It's significant that they can be this bright. So more about supernovae in the next unit, which we are gonna do today, but the pattern of debris that comes off of them is not nearly as interesting as what you see from a planetary nebula. Planetary nebula have all these interesting, complicated patterns. Supernova explosions just give you a spherical, expanding cloud of debris. Because I mean, not all of the white dwarf will have its energy consumed. Most of it will, but there will be some of it that survives, and it will be propelled at enormous velocity off into outer space. So these types of supernovae are so bright, we can see them explode in other galaxies. And this is basically how astronomers know how far away other galaxies are. Assuming, and this is a big assumption, that every type 1a supernova, every supernova that happens because a white dwarf has accreted more mass than 1.4 times the mass of the sun, assuming all of those are equally bright, the moment we see any of them, assuming all these are equally luminous, the moment we see any of them, we can measure how bright they are, and we instantly know how far away they are. So this is the main tool we use to figure out how far away other galaxies are. And because most stars are binary stars, we see these kind of regularly, like a few every day. And there's satellites whose entire job is just scanning the night sky, type 1a supernovas. Every time we see one, they know exactly how much energy it should be putting out. Then they measure how much light the telescope is taking in. They do what is, for astronomers, a pretty simple calculation, and boom, you know how far away that galaxy is. So, you know, supernova, supernova. It's pretty obvious if you're looking at the same galaxy every single day. So, unfortunately, there's more than one way to get a type 1a supernova. We would like it if it only happened when a white dwarf accretes an amount of mass that is 1.4 solar masses. But you can also get one when two white dwarf stars just collide. And that is not equally bright. And that's a problem. Astronomers don't like that at all, not one bit. But it's real. And there's probably data out there where we've assumed that the source of that data is a white dwarf that has reached 1.4 solar masses, but it's actually two white dwarfs that have collided. And likely the initial luminosity that's created is more like 2 to 3 times the mass of the sun, than exactly 1.4 times the mass of the sun. This is part of the noise that astronomy just deals with. So, moving on. Not gonna do Jupiter, gonna move on to high mass stars. And I'm also going to give everybody a 10-minute break because I feel like everybody needs it. So I will be back in 10 minutes. Setting an alarm now. See y'all then. Okay, I guess time is up. So I have two announcements now that we're presumably all here. One, a reiteration. The second, new. Reiteration. The next chapter, the one on high mass stars, the homework only has like 3 questions. And it's excused. I'm removing it from the grade book right after this class is done. Don't even worry about it. But that doesn't mean you aren't responsible for the material. I'm still going to lecture on it right now. And there's at least one quiz question coming up that will directly reference the material I'm about to teach. And I want to make sure I cover, so it's worth it to pay attention. Announcement number 2. It is time for class assessment. So I'm going to email out a link for you to communicate with Napa Valley College about how you feel about this class. I urge you to be honest and just lay it on the line. I like to think I'm a good astronomy teacher, but the semester has been challenging. So if you'd like to say that it hasn't been great, I completely understand. There'll be no form of retribution, no matter what anybody says. All right, on to Unit 11. Like I said, no homework over this, but there is material that will show up in at least one question in the future. So I'm hoping that'll keep all y'all interested. Element of the day: silver, titanium, gold, lots of elements are only made in supernovae. These occur only when the very, very, very heaviest of stars explode, or when star corpses collide with each other. So pretty much every heavy metal element you see and touch is from the explosion of a star. Some are quite rare. All the gold mined total on the entirety of planet Earth would be enough to fill 3.7 Olympic swimming pools, and no more. And while that sounds like a lot of gold, that's it. That's all the gold there is. So I'm quite dismissive about the value of diamonds. Carbon is a super common element. It is one of the elements that stars create more than any other element they create. But gold is truly rare. And so is platinum, so is silver, so is titanium, so is aluminum. These heavy elements have only been birthed either when an extremely massive star explodes or when 2 different star corpses have collided with each other. There is no other source. And so when you reach out and you touch your wedding ring, and it's made of gold, or if you don't have such a thing, when you pick up your Diet Coke, you are touching a surface that was created by the death of a star, or by 2 dead stars colliding. There's no other way to make these elements. So that was your element of the day, of which now you have had 2. Let's go through it. Let's go through the bit that is relevant to the homework. We did all of this in the previous PowerPoints, but this is worth reviewing. Remember, a supernova has a few different effects. It both spreads out heavy elements and also shocks gas clouds. There's a type of nebula out there in the Milky Way called giant molecular clouds, which basically means a nebula that is tainted by heavy elements. There's a lot of them. In order to have a giant molecular cloud, you've had to have incorporated many, many, many different supernova explosions. So a new supernova can shock that cloud and start starboard, at which point these new stars burn off the cloud and shock it and create more starboard. The picture at the top left is super famous. I believe it's called the Pillars of Creation. I'm not entirely sure what the what the pop science name for it is. But take a look at it. There are stars that are being born at the edge of that giant liquid cloud. They will evaporate the cloud away from them and send a shock wave through it that will cause more starbirth, which will then create another shock wave, which will cause additional starbirth, until eventually the entire cloud is completely dissolved. And there's nothing left but a whole bunch of new stars, like you see in the top right. And then eventually, those stars will die. They're stars like our sun. They'll eject a bunch of hydrogen and helium, but mainly hold on to their carbon and oxygen and other interesting elements. But if they're really big stars, they're going to eject a lot more elements than that. And that's the real point of today's lecture, is that I want you to know where the heavy elements in the universe come from. So, in brief, most stars make carbon. We've already covered this. But the really heavy stars get hot enough that they can fuse carbon to make other elements. Like, let's say that shell has a little bit of helium in it. Well, you add a little bit of carbon to a little bit of helium to another little bit of helium, so on and so forth. You eventually get neon. You add more elements, you get magnesium. More elements, you get silicon. This process continues until you reach iron. Here's why iron is a big deal. Chandras are gonna hate me today because I'm gonna be here so late that they aren't gonna have time to clean this board. And the morning professor is gonna complain. I'm very sorry about that. So iron, which has the scientific name of Fe, because of Latin, I have no idea what the actual word is at the perfect cusp where if you add elements to it, you don't get any energy. If you try to break it apart, you don't get any energy. In other words, fusion doesn't work and fission doesn't work. It is as inert from the point of view of being used to create energy as anything else in the universe could possibly be. So, if you want to like toss a piece of helium or hydrogen onto iron, the iron basically interacts chemically in a way where it says, I will accept this new element, and I will grow larger myself, but you must give me extra energy in order to make that merger happen. Whereas every element up to iron will release energy when another element is added to it. So that's why iron is the end. Once the core is iron, the star can no longer effectively create energy. The layers around iron can create energy, but iron is such a problem that the whole star is about to die. And very, 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 very suddenly. So what happens? Well, there's iron. Basically, when you go up on this table, you can get energy. When you go down on the table, you can, when you go up on the table, you can get energy. When you go down on the table, it takes energy. And iron's at the very top. So 4 hydrogen creates 1 helium. Mass has disappeared. Get energy. E equals mc squared. Uranium-235 breaks up into daughter products. Wherever those daughter products are, it's higher than where uranium-235 is. So you get energy out of that. That's energy from fission. Hydrogen combined to be helium would be energy from fusion. Moving upwards releases energy. Moving downwards takes energy. So there's nothing you can feasibly do with iron to make it give up energy. Consequently, the core of the star is just become, for the very first time, cold. Previously, when stars contracted, you ended up with a core that was supported by electron degeneracy pressure, where all the electron shells of the atoms in the nucleus were pressing against each other. And that resisted the collapse. That's not cold, that's hot. When the core is finally iron, that core is cold because anything you can do with iron involves it consuming energy, not giving it up. I'm saying cold from the point of view of nuclear reactions. Iron is consuming energy. The iron core, at the time that a giant star finally makes iron, is still millions of degrees Kelvin at least, potentially billions. I really don't know the answer. But regardless, it's consuming energy, not creating it. So small stars make a certain number of elements, theoretically up to iron. When you have a large star, you can expect that will go through different phases, burning different types of energy. Could burn hydrogen for 7 million years. It could burn helium into carbon for about 500,000 years. Carbon can combine the different elements for about 600 years. Now we're talking about the length of 10 generations in the human lifespan. It can consume neon and make different elements for about 1 year. It can consume oxygen and make different elements for about 6 months. It can consume silicon and make different elements for about 1 day. And the reason it can only make silicon for about 1 day is that given the preponderance of elements that are available to create fusion, the next step after silicon would be iron. When the iron core gets too big, it doesn't have to be all that big, the star collapses upon itself in less than 1 second. It collapses pretty close to the speed of light. So there's a huge, huge, huge contraction that happens super fast. In the core, all the protons turn into neutrons. So we haven't talked so much about atomic structure. Honestly, it's not full on something I want to emphasize in this class. We know that there's protons and neutrons in the nucleus. Protons have the positive charge. Neutrons don't have any charge. The electrons are surrounding the whole thing in an orbit that's much bigger than the nucleus. So every proton turning into a neutron means that every proton is creating an anti-electron. That's gonna take care of the electrons. When an anti-electron meets an electron, they're both gone. And there's additional energy created from that interaction. And it's also going to create a neutrino. So I told you once that a neutrino is perfectly content to go through a light year worth of lead and have more chance of not interacting than interacting. Neutrinos are really non-interactive. But when every single proton in the entire core converts to being a neutron, There are so many neutrinos generated that even though they don't want to have anything to do with normal matter under normal circumstances, they are still the driving force behind the explosion that is a supernova. So supernovas are mainly created by an expanding pulse of neutrinos. Neutrinos don't interact with normal matter excepting under very rare circumstances. They don't want to. And indeed, almost all of them just leave without interacting with anything. But there's so many of them that even given the minuscule chance of interaction, they still create an enormous shock wave. That shock wave blows off all of the outer layers of the star. All of them. They're just gone. Blasted into outer space. So here's some pretty pictures of supernovae. They're quite bright. Like I said, supernovae almost invariably explode in a spherical pattern. Nothing complicated like you see from a planetary nebula, where a star is very slowly off-gassing its outer layers. And that is where all of the other elements come from. I'm going to try to teach you why before I go on to the next slides. So, here's the thing about a neutron. It doesn't really want to be a neutron. If you leave a neutron by itself, it'll turn into a proton. And it'll emit a couple of particles to make that kosher with the universe. If you have a bunch of neutrons flying around, as they do in a supernova to a really surprisingly large amount, then they're gonna stick to other nucleuses. So you've got a nucleus. Let's say it has 72 protons and 120 neutrons. I have no idea if that's stable, nor do I know what element 72 protons corresponds to, because the element is determined by the number of protons. If you leave a neutron alone by itself, not connected to anything, it'll turn into a proton within about a minute, couple of minutes. Happens pretty fast. If a neutron gets attached to the center of the nucleus of another atom, it'll transition much, much, much faster. It's at all energetically stable for it to do so. So let's say that there's 100,000 neutrons coming from this direction and 100,000 neutrons coming from this direction. Some portion of them are going to stick. Some portion of them are going to turn to protons. When they turn to protons, this element will go up on the periodic table of elements. And in case you're thinking that this is some kind of exaggeration, trust me, there's a lot of neutrons flying around in a supernova. And then neutrons, having no charge, don't have a hard time sticking to new nucleuses. It's not like the nucleus is trying to get away from it. There's no positive negative interaction. And then the neutron would like to turn to something else. And that's how you get new elements. I would recommend checking out all my links. Again, I'd like this up on YouTube, so I am not going to actually play them or load them. Notice there's a kind of a sawtooth pattern in terms of the abundance of elements in the universe. This is because hydrogen and helium are so abundant. Because hydrogen naturally turns into helium, helium ends up being the main thing that creates new elements. Helium has 2 protons. So odds are, you're gonna become a new element, you're gonna be hit by a helium nucleus, which is why even numbered elements in terms of number of protons are more common than odd number elements. And then iron itself is super common just because that's the end. You can't do anything with iron. Once you're iron, you're gonna stay iron unless something really extreme happens to you. So, of the elements that make up your body, 65% of you is oxygen, almost entirely is water, by the way, H2O. 18% of you is carbon, which stars preferentially create in large amounts. 3% is nitrogen, which is also created in vast quantities by stars. And it's the majority of our atmosphere, too. Most of our atmosphere is nitrogen, so it's highly available as a building block. And then only a little bit is other elements. I don't know as if these elements are the best things to build a body out of or life out of, but I do know that these elements are the things that stars preferentially make more than other elements. So they're kind of what's available. And that's why you're mostly oxygen, carbon, and nitrogen, and hydrogen. But hydrogen hardly counts. Hydrogen was everywhere, right from the get-go. So you have a supernova, you get new heavy elements, you get new star formation. 99% of the energy gets carried off by neutrinos, which is amazing to think about. 1% gets carried off by the physical speed of the stuff that is shoved away from the core explosion. And 0.01% is carried away by visible light. So it's not a very big percent. If you were to write that number as a fraction, it would be 1/1000th. And yet supernova can, and frequently do, outshine every other star in the galaxy that is hosting them. But it's just a tiny fraction of the energy they're putting out. Almost all the energy is going to neutrinos. Neutrinos don't like to interact with anything, but when you put that much energy into them and you create that many of them, they can still drive a shock wave. So once it's all over and done with, you're left with something called a neutron star. We talked about white dwarfs. White dwarfs are a carbon core that's held up with electron degeneracy pressure, which is a super fancy way of saying that the electron shells are touching and they refuse to share space. It's almost all carbon with a little bit of oxygen. Supernovae leave the core of a star with so much mass, the electron degeneracy pressure fails. From a certain point of view, quantum mechanics itself fails. The electron shells shatter. There's nothing keeping the nucleuses apart from each other besides the fact that they're all positively charged. But everything is so energetic and the physics is so weird that all the protons turns into neutrons and all of a sudden there is no more positive charge. So that's a white dwarf. A neutron star is just this. There's a ton of nuclei basically on top of one another. I told you that the difference between the size of electron shells and the size of the nucleus is about the difference between the size of the planet Earth and the city of San Francisco. The reason I have that analogy is that the size of a white dwarf is about the size of the planet Earth. The size of a neutron star is about the size of the city of San Francisco. So all the protons turn into neutrons. Electron shells shatter. Which is a real failure of quantum mechanics. Fermions, like electrons, should not be sharing space with other fermions, and yet briefly they do. And it all gets super, super, super tiny. In case you're wondering, this is called neutron degeneracy pressure. These things, these particles don't have any charge, but they are still fermions. They don't want to occupy the same space as other fermions. The next line of defense that quantum mechanics has is that the neutrons themselves are saying we will not share the same energy state as other neutrons. And so the thing that's preventing this entire star corpse from occupying just one point is neutron degeneracy pressure. And in case you hadn't guessed, what a black hole is what happens when neutron degeneracy pressure fails. Moving right along, a neutron star is mostly neutrons on the core. It's got a crust, which can be charged, generally is charged. It's got to be at least 1.5 times the mass of the sun, but it's only about 12 miles in diameter. I guess it's a little bit bigger than San Francisco, 7 by 7, right? If a space shuttle tried to leave the surface of a neutron star, it would have to travel over half the speed of light to achieve escape velocity. If you want to leave planet Earth, you've got to travel 10 times faster than a bullet to achieve escape velocity. If you try to leave a neutron star, you've got to travel half the speed of light. And the reason why a black hole has an event horizon, the reason that it has a point of no return, is that there is an orbit around a black hole at which, if you want to break that orbit, if you want to leave the black hole, you'd have to travel more than the speed of light. Since nothing can travel more than the speed of light, you're trapped. So remember ballerinas, the closer you pull your arms in, the faster you spin. Neutron stars go from being pretty darn big to being super tiny. Consequently, they spin very quickly. They also have super strong magnetic fields, and that creates jets to the top and the bottom. Sometimes those jets happen to align with the planet Earth. And when they do, we see boop, nothing, boop, nothing, boop, nothing, boop, nothing. Only we see that like thousands of times every second, tens of thousands of times every second, hundreds of thousands of times every second, because as I said, neutron stars spin fast. All right, so a normal sized star like our sun eventually runs out of helium, runs out of hydrogen in the core, has a helium core, it compresses, is held up by electron degeneracy pressure. You end up with a hydrogen core burning around it, which dumps excess helium into the core till the core gets hot enough that it eventually starts to combine helium to make carbon. And that's the end of that star. Once helium is burning into carbon, all the outer layers puff off, basically, and you're left with a white dwarf. With a really big star, you get many layers. When the core is iron, the star explodes in basically a moment because iron consumes energy. It it doesn't generate it. All of the protons in the core turn into neutrons, and that generates so many neutrinos that even though neutrinos don't want to interact with anything, so many of them are sent out that they basically blast the star apart. And that's where all heavy elements come from. That or something like 2 neutron stars collide. So again, the gold in your ring comes from either the death of a star or else from 2 dead stars colliding. There is no other source for it. And gold is expensive, so the aluminum in your can comes from either the death of a star or from 2 different dead stars colliding. And that's what I got. We're going to deal with black holes later. And I hope to return and talk about globular clusters and open clusters later. But they aren't actually explicitly on the homework. So even though they're super cool, I'm not going to deal with them tonight because demo show. And I'm sorry. This has been an awful semester. I never would have anticipated that the pandemic would have so increased demand for lecture demos. But professors are so desperate to form any kind of connection to the classes, which I completely understand, that they have just been asking for so many demos. And that's what I'm dealing with. And my teaching at Napa is suffering as a result. I apologize. Cal will be done next week, and I hope to make it up to you. Because you came here to learn astronomy, and I'm having to fast forward through this stuff for the sake of catching up. Are there any questions before I go? All right, well, that's where we're at. I'm gonna go tune the beaker to explode. Talk to all y'all later.